I have a ball here, and let's think about what the motion of this ball looks like. If I were to just hold it and drop it, I just let go, what would happen? It would just fall straight down. What if I throw it just a little bit? I throw it horizontally with a small velocity. What happens? It's just going to go forward a little bit, but still fall down. What if I throw it a little harder? What happens? Well, it'll go a little further. What if I throw it harder? Well, it goes a little further before it falls down. What if I were to throw it even harder? It would go farther before it falls down. What if I could imagine I'm outside and there are no buildings or trees or anything in the way, and I throw it very, very fast, as hard as I can. It would go farther before it hit the ground. Let's imagine we could just keep extending that idea. I'm going to draw the Earth, and here I am. Okay, obviously this is not to scale. If I drop the ball, what does it do? It falls straight down. If I throw it a little bit, it goes a little ways before it falls down. If I throw it faster, it goes a little farther before it falls down. Well, let's imagine that we could actually launch it so fast that as it falls, it actually doesn't get closer to the Earth, because the Earth, the surface of the Earth, kind of curves away underneath it. So as the ball falls, it's still falling, notice, but the surface of the Earth is curved away underneath it, so that it continues to fall. But again, the surface of the Earth curves away, and it continues to fall, and continues to fall, until it actually comes back to where it started. We have to assume there's no air resistance or anything like that. Imagine that we could do this up above the atmosphere so that there was no, or at least very, very little, air resistance. That object would just keep falling, but going around the Earth. We call this motion, we say that the object is in orbit. In other words, we have got an object undergoing uniform circular motion where the centripetal force, well, what is the centripetal force? What is the force acting on the object, pulling it toward the center of the motion? Where is the center of the motion? The center of the Earth. What force is acting on the object, always pulling it towards the center of the Earth? It's gravity. It's the weight of the object. So, what keeps an object in orbit around another object is the gravitational attraction between those two objects acts as the centripetal force keeping the object going around in a circle. Very good. Let's stick some variables in here, and then we'll stick some numbers in there. Let's imagine that we have a satellite in orbit around the Earth. So here's the Earth. Here's a satellite going around the Earth in uniform circular motion at some speed v. Let's imagine the satellite has a mass of m sub sat, mass of the Earth, m sub Earth. Remember that astronomical symbol for the Earth. And let's imagine that the orbit has a radius r. We want the force acting on the satellite, the force that's actually keeping it in orbit, which is the centripetal force pulling it towards the center. That force is going to be the gravitational attraction between the Earth and the satellite. So the centripetal force acting on the satellite toward the center of the motion, that is going to be gravity. So we want the centripetal force equal to the gravitational force. Remember, the centripetal force is not an extra or additional force. Some force acting on the object is acting as the centripetal force. It's acting towards the center of the motion that keeps the object moving in a circle. And what is acting centripetally in this case is gravity. So the centripetal force we know must be equal to, we're looking at the motion of the satellite, so that'll be msat v squared over r. The gravitational force we know is gm1 m2 over r squared, so that'll be g, mass of the Earth, times the mass of the satellite over r squared. We can divide off the mass of the satellite from both sides, multiply by one value of r, and that cancels off the r squared, and taking the square root, and we have that v, the speed of the satellite, must be equal to the square root of g, mass of the Earth, over r. Very good. So this tells us what the speed of the satellite must be in the orbit as it's going around the Earth. One particular kind of satellite that is very, very useful are communication satellites. Maybe it would be possible to put a satellite up in space so that it would always stay at the same place above the same point on the Earth. Now, how would that be possible? Well, imagine I'm the Earth and the satellite is going around the Earth, but the Earth is also rotating. The Earth spins on its axis once every 24 hours, once a day, approximately. Well, if that satellite could orbit the Earth once a day, it would always stay at the same point in the sky relative to the Earth all the time. Well, let's see if we can do that. Let's figure out how far away a satellite would have to be in order to always stay above the same point on the ground. That's what we call a geosynchronous satellite. Geosynchronous. It is synchronized with geo, with the Earth. Well, how would we figure that out? Let's remember the period of an object undergoing uniform circular motion is 2 pi r over v. Well, if we know r, we know v, we can put that in there, and we can set t equal to the period that we want to have our orbit to be 24 hours. So let's do that and see what we get. With v equal to root g m Earth over r, and t is equal to 2 pi r over v, we have that t is equal to 2 pi r over v, in other words, times root r over gm Earth. Squaring both sides, we have t squared equals 4, 2 squared is 4, pi squared, r squared times another r gives us r cubed, and then squaring the denominator, g mass Earth. Multiplying both sides by gm Earth and dividing by 4 pi r squared, we get r cubed, sorry, that should be a cube, r cubed is equal to gm Earth t squared over 4 pi squared. Let's assume that we want a geosynchronous orbit so that t is equal to 1 day, the time that it takes for the Earth to rotate. Did I say that the Earth rotates once a year before? What I mean is the Earth, whatever I said before, and I hope I didn't say it was a year, the Earth rotates once a day, 24 hours. I don't think I said 1 year. I hope I said 1 day. We're going to put in t is 1 day, 24 hours, or 8.64 times 10 to the 4th seconds. So we have g, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times the mass of the Earth, 5.98 times 10 to the 24th kilograms, times t, 8.64 times 10 to the 4th seconds, squared, divided by 4 pi squared. That gives us r cubed. Multiply that out, take the cube root, and what we get is r 4.23 times 10 to the 7th meters. Now, that, remember, is measured from the center of the Earth. That's the radius of the orbit, and from Newton's law of universal gravitation, that's measured from the center of each object. So that's from the center of the Earth, which means the satellite has to be that distance minus the radius of the Earth, which is 3.59 times 10 to the 7th meters above the ground level. So we need to put this satellite at a height of 3.59 times 10 to the 7th meters above the ground. And if we were to do that, we would have a satellite that would orbit around the Earth once a day, so it would always appear to be at the same point in the sky. Very, very good. Well, I hope that was interesting. That was uniform circular motion. What we're going to do next time, actually, what are we going to do next time? I have to look ahead. What we're going to do next time is start taking a look at a new way of looking at problems. We will look at problems that Newton's laws do apply, but sometimes Newton's laws can be difficult to apply. We will use Newton's laws to develop a different approach that can be used on some problems where it would be hard to use Newton's laws. We're going to introduce some new concepts, work and energy, and see how those can be used to solve different kinds of problems. Well, I think that'll be interesting. I'll see you next time.